Okay, good morning. So, we will get started from where we had left last time. So, today we will first complete our discussions on what we were doing last class, and then we will start discussing about how to schedule tasks in multiprocessors and distributed systems. So, these are some of the practical issues that we are slowly trying to bring in. First, we had looked at the simple and ideal case of a uniprocessor, task scheduling on a uniprocessor, and then we were trying to bring in task dependencies, and we saw that it is not really very difficult to handle task dependencies. Today we will complete our discussion on that, and then we will start discussing about how to schedule tasks on multiprocessors and distributed systems, because nowadays uniprocessors are slowly going out and being replaced by multiprocessors, and also distributed systems are becoming commonplace. So, with that let us proceed. So, first let us recall what we were trying to do yesterday. We had said that in practical situations some tasks have dependencies with each other, and that is what we had not assumed earlier. We had assumed that the tasks are independent, and then we were saying that the basic scheduling techniques, the table driven, then the RMA and the EDF need to be modified when there are dependencies among tasks. But the idea of handling task dependencies was very simple. The idea was that do not enable a task until its predecessors complete their execution. So, when there are dependencies, first let the tasks which have no predecessors complete, and then the tasks that are dependent on this become ready, because if they become ready before the predecessors are complete, this will compete for resources with the tasks on which they are dependent. We had looked at how to modify task parameters for table driven schedulers and also the RMA. Basically, we are trying to modify the ready time, and we had taken some examples. We found that it is not really very difficult, it is easy actually, unless some of you they want more examples on that, but looks like that it is simple and you do not need additional examples. Concepts are simple on modifying task parameters for RMA. Now, let us try to see how task parameters can be modified for EDF. Basically, we will have to modify the ready time so that a task does not become ready until the predecessor completes, and the predecessor completes when its own ready time plus its execution time is over, right. Just see this parameter, this is for every predecessor for a task. We will have to find out its ready time and its execution time, and check with the ready time. This we can say the phase actually. I could have even written here phase, the phase of task Rj. So, the modified ready time per Rj is denoted by Rj star. It should be equal to or greater than the maximum of these two parameters. One is its phase of the task j, and the other is all its predecessors Ti, its ready time, modified ready time, and the execution time. So, until the task completes, we should not get the successor ready, that is the idea here. And then since the tasks are scheduled based on their deadline, we will also have to do modifications to the deadline of the tasks. This we did not have in the case of RMA. So, here obviously we can't increase the deadline, we can only reduce the deadline, right. If a task completes before its deadline, it is all right, but we can't increase its deadline. Now, first of all, why do we need to change the deadline of the task? Can't we just change the ready time and let it execute?
Deadline cannot be changed because other tasks may be dependent and this may be critical task. So, deadline anyway, this is a property of real time system.
No, the deadline can be reduced. See, what you are saying is deadline cannot be changed. It's not correct, because deadline can be reduced, it cannot be increased.
But even if it is reduced, it is not going to solve any problem.
It will be useful to change the deadline, because here the tasks are taken up for scheduling based on the deadline, right, the earliest deadline. In the RMA case, we change the task priorities. So, even among the ready tasks, we distinguished by priorities, but here we will change the deadline. We will just take some examples and we will say that we need to reduce deadline in some cases where the previous tasks deadline minus execution time is less than this deadline, right. Then this will get a higher priority, a task Dj will have a higher priority compared to its predecessor, which we do not want, right. That is the idea behind this second parameter. So, let us take an example of this one here. If we have a task Ti whose phase is 2, the execution time is 4 and deadline is 20, and a task Tj whose phase is 0, execution time is 5 and deadline is 23. Now, for Tj, let us compute the ready time. The ready time will be maximum of Rj, which is 0, plus Ri star plus Ei, since it is the task which does not depend on anything. Ri is same as Ri star. So, this is 2, Ri is 2 and Ei is 4. So, this becomes 6, right. Rj is 0 and this is 6. So, we have to replace 0 with 6 here. The modified ready time for Tj should be 6. Now, let us say this is 23 is the deadline. Now, 23 minus 5 is 18, right. 23 minus 5 is 18. So, it must start by 18, otherwise it will miss its deadline, is not it?
It must start by,
yeah, by 18, it must start by 18, otherwise it will miss its deadline. So, for this task we have to get the deadline as 18, because if it completes by 20, then there will be a problem here, right. This will miss its deadline if it completes by 20. So, we will have to replace its deadline task Ti with 18, right, and with the Tj's ready time has to become 6. So, that is the modification we will have to do for EDF. Now, let us just try some examples. I hope this is understood, everybody. Now, I will just give an example. Please tell me what will be the modified task parameters. So, let us just draw an arbitrary task graph. So, let me just draw a task graph like this. T1, T2. So, let us assume T1's phase is 5, its execution time is 5 and its deadline is 25. So, those are the task parameters for T1. For T2, let us say it is 0 is the phase and execution time is 6 and the deadline is 30, and the task T3 is dependent on both of these, and T3's parameters are phase is 2, execution time is 4 and deadline is let us say 50. And let us say we have another task T4 whose phase is let us say 10, execution time is 5 and the deadline is let us say 65. Just any arbitrary graph, task graph that I have drawn. Now, let us see whether you have understood how to modify the task parameters for EDF. Now, first let us look at the ready times. So, what about task T1 and T2? Do we need to change their ready times? No, their phase itself is the ready time. Now, what about T3? What will be its modified ready time? What about why the others are not speaking? What will be the ready time for task T3? It will be 10 because that will be a maximum of 2 and 5 plus 5 and 0 plus 6, which is equal to 10. So, let me just write in a different color. This will be modified to 10. Now, what about task T4? What will be its ready time? Yeah. So, the modified ready time for task T4 will be 14 because that will be maximum of 10 and 10 plus 4, 14. Is that okay? So, let me write here 14. Now, that is about the modification to the ready times. But what about the deadlines? We start from the bottom because T4 must meet its deadline, right, that has the longest deadline 65, and then for it to complete we must at least 34 by 60, is not it? So, what should be the modified deadline for T3? So, that will be minimum of 50, 60, which is 50 itself. So, nothing needs to be changed here. But what about T2? Do we need to change its deadline? So, again there is no change to modify its deadline because this is 30, 50 minus 4 is 46, 30, minimum of 30 and 46, which is 30. Do not need to change its deadline. What about this one? This also we do not need to change the deadline, which will be minimum of 25 and 46, right. So, deadlines need not be changed. Just by changing the ready times, we are able to ensure that this precedence ordering among tasks will be ensured during EDF execution. So, I hope that given arbitrary task graph, you will be able to identify what are the changes to the task parameters for it to execute according to the precedence relation. Is that okay? Yeah. So, everybody says yes. So, we will not spend more time on this. Now, let us proceed from here. So, now we will look at scheduling on multiprocessors and distributed systems, because as I was saying that these are becoming very popular. Even the computers in our laboratory are multiprocessors, dual core, and distributed systems are becoming more and more common. So, let us first look at some of the characteristics of these systems, some basic ideas about this, and then we will proceed from that point. So, if we look at a broad classification of parallel computers, because as I was saying that even though so far we studied uniprocessors and they were quite simple, straightforward compared to parallel computers, but slowly uniprocessors are getting replaced with multiprocessors and distributed systems. So, let us look at some of the characteristics of this. So, there are mainly two types. One are the shared memory multiprocessors, shared memory computers which we will call as multiprocessors, and distributed memory computers which we will call as distributed systems. So, the shared memory multiprocessors are also called as uniform memory access computers. Why is that? What is the implication? I mean, why are these called as uniform memory access computers?
So, time to access the memory, primary memory, so time to access the primary memory from all the processors will be constant same.
Yes, that is the idea here. The memory is shared. See here, the main memory is shared, and since it is shared, the time to access the memory, that is for read and write operations, all processors take same time, similar time. So, this is uniform memory access. The time for every processor is the same to access the memory, because that is a shared. On the other hand, the distributed memory computers are called as non-uniform memory access computers, because these are implemented, each computer has stores part of the memory. See, the memory is distributed. See here, the memory is distributed among different processors, and therefore, the access time to the memory depends on whether it is local main memory we are talking of, or it is the memory that is present with some other processor that you are talking of. So, the time can vary widely from few milliseconds to few seconds, depending on where the memory is located. And there are variations of this distributed shared memory architectures. So, distributed shared memory, this is done for simplification of programming basically. Here the memory is distributed, but the operating system makes it appear to the application program that it is a shared memory, just a operating system facility for programmers, because programming shared memory computers is easy, just keep on writing just like you used to do for uniprocessors, and the operating system takes care of where the memory is located and generating appropriate commands to do the read and write operations. And we have the clusters and grids etc., which are becoming popular. So, this is the schematic diagram of a uniform memory access model, which is a multiprocessor. So, we have the different processors have their own cache, and the main memory is shared. So, that is what we mean by the shared memory. The main memory is shared, and they are interconnected by a high speed bus. On the other hand, in a distributed system, we have a non-uniform memory access model, where the different processors have their own cache and main memory, and they are interconnected by a network. So, a processor needing data from its own memory will be very fast, whereas if it needs data from another main memory, it depends not only on the access time for this main memory, but also the network delay, right. So, the latency here is several milliseconds to seconds, depending on where the memory is located, whereas here it is about a millisecond or maybe hundreds of nanosecond. So, this is just a different schematic for a distributed system. The network, typically we talk of a wide area network, but it can be also a local area network. A distributed system can also be implemented on a local area network, where we have different nodes which typically are heterogeneous nodes. So, that is why we have shown them in different colors. Some may be desktops with Windows, maybe some may be Linux computers, etc. The distributed computers use a message passing model, and here the programmer has to write explicit send and receive instructions, right. Whenever the data is located on a different processor, needs to write receive and send commands. And the advantages of message passing communications are many compared to a shared memory. Even though shared memory, we said that it is very simple to program, but message passing communication has its advantage. One is that the communication and synchronization is simpler. Actually, during every message passing, synchronization takes place, is not it? Because unless the receiver is ready, the sender can't send. So, implicitly there is a synchronization during every message passing primitive. Whereas in a shared memory, it does not matter whether the other process is ready or not, it just modifies it. Here the message passing makes the programs easy to understand, because you know at what instant communication occurs with which process, etc. But in a shared memory computer, it just modifies, a process modifies its data, and it may be any process which accesses. It is not clear actually, just by looking at the program, it is very difficult to deduce that after a change occurs, which other process will access it, read it and modify it, which will read first, etc. But here it is explicit, it will name the process to which the data will be sent, it is there explicit. The synchronization is implicit, easier to debug, but there are also disadvantages with the message passing communication. That is why you will find that multiprocessors are possibly used more heavily than distributed systems. One is programmer does extra job, writes message passing constructs. You have to precisely identify the process to which communication is to occur. And when there are dynamic creation of processes, etc., you will have to keep track of the process IDs and then communicate with them. And also each time there is a message passing, you will have to give an explicit call to the operating system, which is a higher overhead. So, that way you can argue that shared memory programs are more efficient compared to message passing programs. But let us see why the distributed systems and multiprocessors, they are becoming more and more important in real time applications. First, let us look at the distributed systems. In many applications, the application itself is distributed. For example, there might be sensor collecting data from different locations, right, physically separate locations, and you can't really transfer all the data to a central processor and then execute it. What really happens is that these are processed locally near the sensors, and then summary data is sent to the computer, and even there it need not be just one processor which takes action. It may be different processors which are there, which handle different aspects of computation. Many examples are there: command and control, air traffic control, etc. Another reason why distributed systems are becoming popular is their higher performance, because the workload by definition is distributed among multiple nodes, and also fault tolerance can be easily implemented here. It can be different nodes, and one node fails, other nodes take up from that point. And whereas in a uniprocessor, if the processor fails, the system fails, right, single point failure can occur. But before we look at the distributed systems, let us also understand what are the problems with the distributed systems. One is resource management is difficult, because at any time we do not know what are the workload of different processors. It is very difficult to keep track instantaneously what is happening in different processors, because even if they exchange their information, but still by the time it comes and reaches, it will become obsolete. And also you can't just keep on transmitting what is the load position at different nodes, that will be too inefficient. So, we will have to, if at all, transmit the load positions once in a while, right. So, that means you have a obsolete information about the load position on different nodes. So, once a task arrives, where it needs to be executed is a very difficult question, because you have to work based on only obsolete information. The system's information might be that some node is relatively free, but if the task is migrated to that node, find that that node has already got lot of work very recently. So, that assumption may be wrong because of the stale information. So, this is a big problem. We will see how to address this. There is no satisfactory solution to this exists. It is a problem inherent to all distributed system. Global knowledge about the resource uses and the load at different nodes does not exist. The global information that is current or accurate does not exist, only at best we can have some stale information, right. Okay. So, that is one problem. Another is that in a uniprocessor or in a multiprocessor, the clock is one, but here each node will have its own clock, and synchronizing them is difficult. We will see the problems in clock synchronization. And then also a distributed system needs to address the communication problems. The packets might be delivered out of date, out of order. There may be total loss of packet, not only the packets are delayed out of date, but they can also be lost. So, these corrective actions need to be taken, and if the task is a real time task, then it makes it more complicated. What to do when there is a packet loss, for example. And in a distributed system, it is very difficult to identify intermittent node failures. You do not know whether it is due to a congestion that you are not able to communicate with a node, or is it that it has actually failed intermittently, right. So, very difficult questions here we have to address, and we will see that as a result the scheduling solutions are also very difficult compared to a uniprocessor. Okay, let us proceed. Before we look at the scheduling, let us look at the system model. The tasks arrive at each node independent of the other nodes. So, that means the sensors, for example, are distributed, they collect different data or maybe same data from different locations, and the rate at which the tasks get generated at that node is independent of the other nodes, because they get different types of data at different rates and from different locations. And typically each node will assume that it has a resource manager. The responsibility of this resource manager is to manage the workload at the local node. When the tasks arrive, it will try to check whether it can be processed locally, and if not, this resource manager would have to find out where to transfer this task, that is migration problem. And we will also assume that the nodes will cooperate among themselves, they might exchange messages, other information, they might honor requests from other nodes for migration, etc., to meet task deadlines. So, that is the basic assumption we will make as far as the system working is concerned. We will also make some assumptions regarding the workload The workload will be a mixture of periodic and aperiodic tasks. The tasks can have precedence constraints, specific resource requirements and also specific fault tolerance requirements. And for simplicity, we will assume that the message transmission times are constant and bounded. We know that this is not true actually, because messages depending on the load congestion, they might take very different times in a wide area network. But we will right now assume that we have some protocols which will ensure that transmission times are constant and bounded. Towards the latter part of this course, we will see how this can be achieved. We will not be able to achieve 100% a constant and bounded, but for specific tasks, we will call this as the quality of service for communication, and we will see that constant and bounded quality of service we will try to ensure through use of proper suitable protocols. Okay. So, let us look at a broad classification of the task scheduling solutions. We have broadly two categories of solutions. One is a static solution. In a static solution, we predetermine which task will run on what processor and using what algorithm. The static solutions. The tasks are statically assigned to the processors. On the other hand, we will discuss another category of solutions, which is the dynamic solution, where once the tasks arise, it will be each time decided where the task will execute. Will it execute on local node? Will it execute on node X or node Y? That will be decided on a task to task basis. Of course, the static schedulers are simpler. It is done just once, but the static schedulers, they can't really handle when the tasks themselves are not static. See, if the tasks are nice periodic tasks and we know where they are coming, etc., we can use a static solution. But what if we do not know when the tasks will arise and how many of them will arise, etc., we do not know, we can't really use a static solution, isn't it? We can also have another classification, that is local scheduling versus global scheduling. In a local scheduling, the resource manager will be associated with every node, and which will look at whether the task can be executed locally or need to be transferred to another node, etc. So, that is for every node, the decision will be separate based on a local scheduler, a resource manager that is running on the node. Every node have a resource manager. On the other hand, in a global scheduling, we will have just one node decide about what to do. Once the task arises, this is the one which will run somewhere and it will decide what to do with that task, where to send. So, obviously, what is assumed here is that the global scheduler has knowledge about what is the resource position at resource utilization position at different nodes, and we had said that it is very difficult to have a global state information, and as a result these global schedulers have their limitations, and the ones that we will discuss, the solutions are local scheduling. Global scheduling has its disadvantages. Now, let us look at what type of schedulers to use, whether it is static or dynamic. It is not surprising, it would not be surprising to know that all multiprocessors and distributed systems that are commercially implemented use a static scheduler, because these are easier to implement, you can ensure time constraint and so on. The dynamic solutions are more complex, higher overhead, but that is the situation right now. We do not know about maybe few years from now, we can have the dynamic schedulers also being used heavily. because the tasks are becoming more and more complex, task characteristics are becoming complex, which we may not be able to handle with static schedulers. So, even if these are high overhead, okay, let me just ask this question, that why should the dynamic solutions have high overheads compared to static schedulers? Why should dynamic schedulers have high overhead? We have written here, they involve higher overhead compared to static schedulers. What do you think? Why do these have higher overhead?
But if instance we have to say how many processors are ready for execution of like that.
Any other?
These dynamic solutions will involve high information exchange and repeated computation.
Okay, any other answer?
There was context switching and
Not really. See, the thing is that, see, static one is just done once, isn't it? It's just done, and whereas a dynamic one, we need to have several types of information exchange. The system state has to be with every resource manager locally, and then as the task arrives, decision has to be done, right, and the task might have to be migrated and so on. It has to done for every task, whereas in a static one it is just done once for all, right. So, that is the main reason. Okay, let us proceed. In these multiprocessor and distributed systems, the scheduling problem is actually two separate problems. For uniprocessors, we had seen that the scheduling problem is only when to schedule the task, when the task will start. But here in all multiprocessor and distributed system, we will not only have to decide when a task starts, but before that we have to decide which node or which processor the task will run. That is the first thing, and then once it has been assigned, we need to worry about when it will start on that node. So, the assignment to a processor is the first problem that we need to worry about. We will call it as the task assignment problem, which will basically deal with how once a task arises, which node it should be migrated to. Should it be run locally at some node or should it be migrated to some node? That is the task assignment problem. And then is the scheduling problem. Once the assignment is done, we know that which node it is going to run or which processor it is going to run. Then we worry about when it will run. But what about optimal schedulers for multiprocessors and distributed systems? Please recollect that when we were discussing about uniprocessors, we were actually saying that, see, there are large number of algorithms proposed, and we said that there are optimal scheduling solutions exist, and if we know that, we know more or less about that area. And for static task scheduling, static priority scheduling, which was the optimal? Yeah, rate monotonic algorithm was the optimal. We had said that if any scheduler can schedule a set of tasks successfully, then RMA can schedule, but whatever RMA can schedule, the other scheduling algorithms may not be able to schedule, right. And similarly for dynamic priority, we had identified EDF and we had studied these two algorithms, and we said that if you know this RMA and EDF and also the deadline monotonic algorithm, because that is for different task characteristic, that is optimal. But unfortunately for distributed systems, we will see that no such optimal solutions exist. Let us see the reason and what is the status here. If there were optimal schedulers existing here, we could have just studied one or two algorithms and said that, see, these are the optimal schedulers have to be used, and we will have to do that, but here no such clear cut answer here. Let us see the situation here. We had seen that for uniprocessors, as far as static priority schedulers discussed about RMA, the optimal scheduler. For dynamic priority, EDF was the optimal scheduler. And then we studied about their complexities. What is the complexity of RMA, by the way? I am saying runtime complexity, time complexity of RMA. So, what is the, you have to look at the algorithm, what are the steps it does, right, and based on that you have to compute the runtime complexity, isn't it, time complexity. So, what are the steps in RMA? So, once a task arises, what you need to do?
Scheduling time.
You have to arrange the order of priority.
Okay. So, the tasks are in order of their priority, is it? So, is that a queue, or I mean how will that be implemented? But why a queue? We had discussed about the implementation of RMA. I hope somebody remembers that. How is the?
Use heap for that. Maintaining the priority heap.
Any other answers? Please recollect, you possibly will have to revise little bit. See, we had said that every operating system has a set of discrete priorities, right, and here in a rate monotonic algorithm, it is not the deadline, like some of you were trying to say that, see, you will have to examine the task queue each time. No, it is basically we have to scan through these priority list. So, if there are 16 priorities, check whether priority 1 tasks exist, execute them. There are no priority 1, execute priority 2, right, and for every priority we just order the way in which the tasks arrive, first in first out, right, for different priority levels. So, what will be its complexity? There are only a finite number of priorities, 16 or 8 or maximum 32, we will discuss about 32 priority systems. And then you will have to, each time a task arises, you have to scan all these levels. The first one you find a task, the highest priority level, execute it. So, what will be the complexity? Yeah, it is a linear complexity. It is a linear complexity for rate monotonic and log n for EDF. Okay, it will be n log n, I am sorry, it will be n log n because this will be for every task, right, n log n, I am sorry, I have done a mistake here. But unfortunately, for real time task scheduling on multiprocessor and distributed systems, this is a NP hard problem. It has been proved and papers have been published. If you are interested to show how to show about real time task schedulers are NP hard, you can just search it on the Google, you will find enough papers where they show different types of systems, different types of task characteristics and how they have been shown to be NP hard. Those who are more theoretically inclined, they can check for proof for NP hardness, but right now we will just assume that the tasks are NP hard, the schedulers are NP hard, the scheduling problem is NP hard. Now, first look at the task assignment problem, because we had said that task scheduling in multiprocessor distributed systems, the task assignment is the first problem we need to worry about, and having done the task assignment, then we will worry about task scheduling problem. So, the task assignment problem, there are actually two types of solution. One is the static solution and the other is the dynamic solution. So, let us see these details about these solutions. We will discuss 3 algorithms actually on the static task assignment solution. These are utilization balancing algorithm, next fit algorithm for RMA and the bin packing algorithm for EDF. So, the next fit algorithm will be used when the nodes themselves are scheduled using RMA, and the bin packing algorithm will be used when the nodes themselves. So, these are the scheduling algorithms to be used in the individual nodes, and this is the task assignment which will be used in conjunction with this scheduler. We can't use a bin packing algorithm per RMA because it will not work, we will see why. And then we will look at the utilization balancing algorithm, which will see that we can make it run with RMA and EDF both. We will just examine this algorithm. And then we will look at two categories of dynamic solutions: the focused addressed and bidding algorithm and the body set algorithm. Here this distributed task scheduling, task schedulers for distributed and multiprocessor system, thousands of algorithms have been proposed, mostly based on heuristic. We will see that these are all heuristic because the problem is NP hard. We will have heuristic solutions, just try to, based on some assumption, we just try to check how they are performing for specific systems and task characteristics, but optimal solutions do not exist. And as we were saying that the uniprocessors, most of the results were available in the 1970s, and some results we had seen in 1980s also, Liu and Lehoczky's criterion and so on. But here the research started actually in 1980s, and even now you will find that many research papers are getting published here. PhD degrees are awarded for real time task scheduling on multiprocessors and distributed systems. And now that we have the multi-core computers which are becoming commonplace, so that is again another hot area for research in developing suitable task schedulers for real time tasks. First, let us look at the utilization balancing algorithm. The idea is very simple here. We maintain a queue. The queue will contain the tasks in increasing order of their utilization. Obviously, we are assuming that they are periodic tasks, right. Then we can compute the utilization. Remove tasks one by one from the queue. So, the first task in this queue will be the one having lowest utilization, and the last task in the queue will be having the highest utilization. And how is the utilization defined? Utilization per a task? Yeah, EI by PI, execution time over which period. So, after PI the next instance of the task will occur. So, for during every PI you need EI for to execute this task, or in other words it will keep the processor busy for EI by PI fraction of time, right. So, that is the utilization. So, remove the tasks one by one from the queue. First take out the task having the lowest utilization and then allocate it to the lowest utilized processor. So, we will also have the processor status information. We just take one task, then examine all the set of processors, we might have 4 or 2 or something, and then check which is the processor. Okay, I have written here process, should have been processor. Check which is the lowest processor at that instant and then allocate it. Of course, for the first task from the queue, both the processors will have 0 utilization, it can be allotted to any one of them, but then the second one naturally will have to allocate to the one which has 0 utilization, and from the third onward we will just compare, keep on comparing the utilization for different processors and then allocate that. But unfortunately in this algorithm it is very difficult to achieve the loads or the utilization of the individual processors equal to the average utilization. See, if you have n tasks, then the average utilization of the processors will be sigma ui by n, is not it? See, if each task, okay, I think also using the ui symbol for the processor utilization. Okay, let me just say that the utilization for a task is, let us say, TU. So, the utilization due to all the tasks will be sigma TU, right. So, if we have a perfectly balanced load, then we will have sigma TU by n should be the load for every processor. But unfortunately, here we will have a variation of load among different processors. Some load will be more loaded, some processor will be more loaded than other processors, and therefore, we are saying that u bar, which is the average load, will not be equal to the individual nodes. That is actually the figure of merit for any balancing algorithm. So, here if we do not restrict the utilization for the number of nodes, it can only be used for EDF. See, if we say that, see, we go on assigning tasks until there is certain utilization achieved, it can only be used for EDF. Why? Because anybody would like to answer before I answer? Why is it that if in this form of the algorithm, it can only be used for EDF? Yes, anyone wants to answer this question? Answer is simple actually. See, here we are just trying to balance the utilization, but you know that in RMA, the schedulability criterion for real time tasks is that there is a bound on utilization that is dependent on the number of tasks and that are allocated to the node, and we had looked at the Liu Leland and Liu Lehoczky's condition. And here in this utilization balancing, just check that we have not really followed any of those constraints of Liu Leland or Liu Lehoczky. So, this algorithm will not work for RMA in this form, is not it? We are just worried about how to balance the load. So, it might happen that some node has 0.9 utilization and another node has 0.8 utilization. It will ensure that EDF they can be run on EDF as long as the utilization is less than 1. But for RMA, this algorithm will not work in its current form. So, how do we need to change this algorithm to work for RMA? So, please think about it. How can the utilization balancing algorithm be modified such that it will work for RMA? So, we will just take a short break for the next class before we start about discussing other static scheduling solutions and also the dynamic scheduling solutions for distributed systems, right. So, okay, we will stop here.